In this lesson, we're going to talk about angles on the Cartesian plane. In other words, angles on the x and y axis. First thing we want to know is what standard position means. That's when an angle has one arm along the positive x-axis and the angle's at the origin. The other arm's called the terminal arm. For a positive angle, we rotate counterclockwise from the positive x-axis, and for a negative angle, we rotate clockwise from the positive x-axis. So this would be an example of a positive angle, and this would also be an example of a positive angle. Now, we can talk about radians and degrees. Most of us used to degrees, but radians are also important. A radian, if you're curious, is the angle that is present when the length of an arc is equal to a radius. And no matter how big the circle is, the size of the angle created in that instant will be the same. It's roughly 57 degrees, but mathematically we call it 1 radian. So suppose we wanted to convert 300 degrees to radians. Well, we know that 300 degrees is equal to 300 degrees times 1. Well, we can say that 1 is equal to pi over 180 degrees. The reason being that pi radians is 180 degrees. So pi equals 180 degrees. So the fraction of pi over 180 is equal to 1. So we end up with 300 pi degrees over 180 degrees. The degree symbols cancel out. 300 pi over 180 is equal to 5 pi over 3. So 300 degrees is equal to 5 pi over 3 radians. 2 pi over 9 radians is equal to 40 degrees because we multiply 2 pi over 9 by 1. But in this case, we let 1 be 180 degrees over pi. And when we do that, we get 360 pi degrees over 9 pi. The pi's cancel out, and we get 360 degrees over 9, or in other words, 40 degrees. So a short little thing to remember is that when you convert from degrees to radians, multiply by pi over 180 degrees. But to convert from radians to degrees, multiply by 180 degrees over pi. Now let's talk about trig functions in the unit circle. The trig functions sine and cosine are defined in terms of the coordinates of points lying on the unit circle x squared plus y squared equals 1. When we say unit circle, we mean a circle with a radius of 1. So what we do is we're going to start by constructing a ray from the origin at angle theta, and we're going to say that this ray meets the circle at the point xy. The cosine of the angle will be the x coordinate of the point we get. The sine of the angle will be the y coordinate. Okay? And so as the angle changes, the coordinate on the outside of the unit circle changes, and so cos theta and sine theta also change. So this is what we mean. When we draw a circle with a radius of 1 at the origin, then any point on the outside of that circle will give us the cos and the sine of the angle in the interior. So that's really a very useful property. So this is what the unit circle looks like in radians, and this is what the unit circle looks like in degrees. So let's look at one of them in particular. Let's say at 30 degrees. We look at that terminal arm at 30 degrees, and we see that it meets the circle at the point root 3 over 2, comma 1 over 2. Well, look above where it says cos, comma sine. What that means is that the cos of the angle on that terminal arm is root 3 over 2. Well, the angle on the terminal arm is 30 degrees, so the cos of 30 degrees is root 3 over 2. The sine of 30 degrees is 1 over 2. All right, so let's switch it up. Let's go to, let's say, 240 degrees. Let's look at that one. Well, if we look at that one, the x-coordinate is negative 1/2 and the y-coordinate is negative root 3 over 2. Well, that means the cos of 240 degrees is negative 1/2, and the sine of 240 degrees is negative root 3 over 2. And going back, we see that we can convert each of those degree measures into radians. And so we could go through the steps, but these are the radian measures that we would get. And so we can also express our unit circle in radians or in degrees. And it's a very useful thing. So learning the unit circle is important, and you want to try and memorize it. So that seems like a daunting task, but it's not really. Let's look at this. Let's look at one way of memorizing the points on the outside of a unit circle. What we can do is draw the x and y axes and put a unit circle at the origin. So what we've drawn there is a y-axis and an x-axis, and that circle, the blue one shown, has a radius of 1, and it's centered right at the origin. Okay, now watch this. What we're going to do is we're going to draw all 30-degree angles. So you see there we've got 30 degrees, 60 degrees, 90 degrees is already shown, 120, 150, 180 degrees was already shown. And we go all the way around the circle. Okay? So that part's easy. Now, let's also do multiples of 45 degrees. So starting at 0 degrees, if we go 45 degrees, we get to that one new angle there in the first quadrant. And then if we get to 90 degrees, that's the y-axis. And then if we get to 135 degrees, that's now shown. So what we've done is we've put on our unit circle every angle that is a multiple of either 30 or 45. Okay, so far that's pretty reasonable. Now, what we do is we put down the points 1, 0, 0, 1, -1, 0, and 0, -1. Those are kind of easy to remember. Okay, we're going to be able to remember those points. Now, what we then do is we put all the rest of them, all those other 12 points, give them a denominator of 2. Just do it. Give them a denominator of 2. Now, every numerator will either be positive or negative, and every numerator will either be root 1, root 2, or root 3. And root 1 is the same as just 1. The square root of 1 is 1. So in other words, what we're saying is every single numerator is either 1 or root 2 or root 3, or -1, negative root 2, negative root 3. All right. Well, let's take a look at that first quadrant there. Let's focus on those x coordinates. Look at how we now have in the x coordinates the numerators. The one with the smallest x coordinate in that first quadrant is 1 over 2. The next one is root 2 over 2, and the next one is root 3 over 2. Looking at those x coordinates, that makes sense. They are getting bigger as we get farther out to the right. But now look at the ones in the left in quadrant 2. It's -1, negative root 2, negative root 3. They're getting a greater magnitude as we go out farther from the origin. And that makes sense. Now you might say, well, how do I know they're negative? The answer is because they're x coordinates. X coordinates are negative out there. Now look at the bottom in quadrant number 3. As we get farther to the left, we have -1, negative root 2, and negative root 3. And finally, back in quadrant 4, it's 1 and root 2 and root 3 again. They're positive. Okay, well now take a look at the y coordinates in quadrant 1. Well, the y coordinates, the y coordinate that's labeled 1 over 2, that's the one that's the lowest. And so that's the one that's got the 1. Now the next one up has got the root 2, and the next one up's got the root 3. And now when we go to the other one, we have root 3 and root 2 and 1. And you might say, well, how do I know they're positive? The reason is because they're y coordinates and they're above the x-axis. But now when we go below, we're going to see that they become negative, and we see that they're negative there as well. And so isn't it beautiful? Look at that. It's not that hard to really memorize it. Okay, and then let's talk about tan theta. Well, tan theta is sine theta over cos theta. That's a trig identity that we learned in grade 11. Now, because sine theta is the y coordinate and cos theta is the x coordinate, we can say that when we're talking about the unit circle, tan theta is really y over x. All right, now there are also 3 secondary trig functions. We might say, okay, well, we're always talking about sine, cos, and tan. There's also cosecant, secant, and cotangent. Okay, Now, cosecant theta is the reciprocal of sine theta, secant theta is the reciprocal of cos theta, and cotangent theta is the reciprocal of tan theta. So when we're talking about the unit circle, we can say cosecant theta is 1 over y, secant theta is 1 over x, and cotangent theta is x over y, because those are the reciprocals of the primary trig functions that you already knew about. Okay, so in other words, when we're looking at the unit circle, this is an important slide. You want to know these formulas really quick. Okay, sine theta is the y-coordinate, cos theta is the x-coordinate, tan theta, we just divide the y-coordinate by the x-coordinate. For cosecant theta, it's 1 over the y-coordinate, secant theta is 1 over the x-coordinate, cotangent theta is x over y. So if you can remember those points on the outside of the unit circle, you don't really need a calculator and you can give precise answers rather than decimal approximations. So what if we were asked to determine all 6 trig function values for the angle 5 pi over 3 radians? Now we don't want to have any decimal approximations, and we're not rational, and we want to rationalize our denominator. So what we're going to do is we're going to look at the unit circle. Now remember, what we're looking for here is 5 pi over 3 radians. So look at 5 pi over 3, where that angle is. We see that the x-coordinate is 1/2 and the y-coordinate's negative root 3 over 2. So we can say that the sine of 5 pi over 3 is that y-coordinate of negative root 3 over 2, and the cos of 5 pi over 3 is that x-coordinate of 1/2. The tan of 5 pi over 3 will be the y-coordinate over the x-coordinate, sine over cos. Well, that's negative root 3 over 2 over 1 over 2. And when we invert and multiply, we get negative 2 root 3 over 2, or in other words, negative root 3. So we've just used the unit circle to help us figure out that the tan of 5 pi over 3 radians is negative root 3. Well, the cosecant of 5 pi over 3 radians will be 1 over the sine of 5 pi over 3 radians. 1 over negative root 3 over 2 means we want to invert and multiply, and we get 1 times 2 over negative root 3, which is negative 2 over root 3. But we want to have rational denominators. So what we do is we multiply numerator and denominator by root 3. We're allowed to do that. And that gives us negative 2 root 3 in the numerator. The denominator becomes square root of 3 times square root of 3, which is also called 3. Now we have the secant of 5 pi over 3. That's the same as 1 over the cosine of 5 pi over 3. 1 over 1/2 equals 2. And finally, the cotangent of 5 pi over 3 is 1 over the tan of 5 pi over 3. 1 over negative root 3 is the same as negative 1 over positive root 3, but we want to rationalize our denominators. And we also want to, if there's a negative sign, put it in the numerator instead. Now, what if we have, what does it mean to be a coterminal angle? Well, coterminal means 2 angles share a terminal arm. So, for example, look at the first angle shown there. Look at that angle, the black one. If we start at the positive x-axis and rotate counterclockwise 110 degrees, we end up on that terminal arm. All right, good enough. Well, what if instead of going 110 degrees, what if we do an additional 360 degrees? Well, that's what we're showing with that red one. With that red one, we're going the full 110, but then another 360 to give us 470. And now both of those are positive because they're both going counterclockwise. And we see that a 470 degree angle gets you to the same place as 110 degrees. We don't say that they're equal. They're not. 110 degrees does not equal 470 degrees, but they both get you to the same terminal arm, so we say they are coterminal. Now, how about that green one? Well, that green one, what's different about it is it's going in the negative direction. It's going clockwise. They're all starting at 0. Every one of them starts on the positive x-axis, so they're all starting at 0, but it's going in the negative direction. So negative 250 degrees, we see, gets us onto that same terminal angle. Well, algebraically, we know that 2 angles are coterminal if they differ by a multiple of 360 degrees. So for instance, the red angle minus the black angle is 360 degrees, and they're on the same terminal arm. The red angle minus the green angle is 720 degrees. That's a multiple of 360, so they share a terminal arm. They're coterminal. And finally, the black angle minus the green angle is 360 degrees. We did it again. We got coterminal angles. And it also works with radians. We see that the angle 4 pi over 3 in black would be the same as the red angle of 10 pi over 3, which would be the same as the green angle of negative 2 pi over 3. Well, if coterminal angles differ by a multiple of 360 degrees when measured in degrees, they certainly differ by a multiple of 2 pi when measured in radians, because 2 pi radians equals 360 degrees. So we see that the red angle minus the black angle is equal to 2 pi. And similarly, every other subtraction nets a multiple of 2 pi radians. So these are all coterminal. None of those angles are equal, but they all happen to share a terminal arm, so we call them coterminal. Now, what if we wanted to determine whether these two angles were coterminal? 417 degrees and negative 663 degrees. All we do is subtract, and we see that they are a multiple of 360 degrees apart. So they're coterminal. But these two angles, 525 and 1715 degrees, they're not, because the difference between them is not a multiple of 360 degrees. How about these two strange-looking radian angles, 62 pi over 9 and negative 28 pi over 9? Well, when you subtract them, you get 10 pi. That's a multiple of 2 pi, so they are coterminal. But the angles 33 pi over 7 and negative 5 pi over 7, they differ by 38 pi over 7, which is not a multiple of 2 pi, so they are not coterminal. Now, another term we should know is principal angle. Every angle has an infinite number of coterminal angles. Okay, so for instance, the angle 30 degrees, I could go another time around, it'd be 390. I could go another time around, it'd be 750. Another time around would be 1,110 degrees. So we could see we could keep doing this all day long. There's an infinite number of coterminal angles. But one of them is the principal angle. Well, how do we know what it is? What it is it's the first angle you get to when you begin rotating positively. So in the case of the angles 30 degrees, 390 degrees, 750 degrees, etc., the principal angle is 30 degrees. Now, if we have an angle of 0 degrees, we say that's the principal angle. If we have an angle of 360 degrees, we say the principal angle is 0 degrees. But otherwise, it's just the first angle you get to when you rotate in a positive direction from the positive x-axis, okay? And with radians, it's the same thing. So what if we wanted to determine the principal angle for the angle 898 degrees? Well, that's not between 0 and 360. So we subtract 360 degrees, we get 538. Still not between 0 and 360. Subtract 360 again, and we get 178 degrees. What we've just shown is that 898 degrees is coterminal with 178 degrees. Don't say that they're equal, but they are coterminal, and we can say that 178 degrees is the principal angle of 898 degrees. If we have negative 722 degrees, we see that we're not between 0 and 360, but to get there, we better add. So we add 360 degrees 3 different times, and we get 358 degrees. That's our principal angle. But they're not equal. They're just coterminal, and one is the principal angle. 27 pi over 5 is greater than 2 pi, so we subtract 2 pi, taking into account the common denominator that we need, and we say the principal angle of 27 pi over 5 radians is 7 pi over 5 radians. And if we have negative 19 pi over 12, we add 2 pi to get to 5 pi over 12, and we can say that those two angles are coterminal. Now, what if we extend beyond the unit circle? Well, recall that we had this set of formulas when we were on the unit circle, and we said, you know, these are important. You should remember these. Well, using similar triangles, we can provide for formulas when the length from the origin to the point is greater than 1. And when we do that, we end up saying these are our formulas for our 6 trig functions when the radius is not 1. You'll see what this means in a second, but we can say sine theta equals y over r, cos theta equals x over r, tan theta still equals y over x, And we have formulas for our secondary trig functions on the right-hand side. So what does this mean for us? Here we go. Suppose I told you that there was an angle in standard position, and the terminal arm, if I extended that terminal arm out, it eventually goes through the point -6, 4. So you picture yourself, you got an X and Y axis. Now picture you, from the origin, you draw a line out to the point -6, 4. What I'm saying to you is, what is the angle created there? Well, what you're going to do is you're going to figure out what does R equal. We know X is -6, we know Y is 4. We're going to figure out what R equals, and then once we figure that out, we're going to be able to use these formulas right there. Okay, well, R is always equal to the square root of x squared plus y squared. R is always a positive value. So R would be the square root of 36 plus 16, which is the square root of 52, which when we simplify is 2 root 13. So we can say sine theta is y over r. Well, remember, going back, the y coordinate is 4, and the x coordinate is -6. So, and r is 2 root 13. So now we just plug them into the formulas. Y over r is 4 over 2 root 13. We can cancel the 2's out. The factors of 2, we get 2 over root 13. But we want to have rational denominators. Multiply top and bottom by root 13. The square root of 13 times the square root of 13 is 13. And 2 times the square root of 13 is 2 root 13. We follow a similar procedure with cos theta. With tan theta, y over x is 4 over -6. That's just simply -2 over 3. When we have a fraction that's negative, we put that negative sign in the numerator. Cosecant theta is root 13 over 2. Secant theta is negative root 13 over 3. And cotangent theta is negative root 3 over 2. And that is the end of our slideshow.